Good evening, Umesh. Okay, we'll get started. So I'm going to cover the week 5 here. Just wait a minute. Come on. So these are the questions we are having. So you're given a matrix and a vector, you apply the transformation. So in this week, there are no deep learning as such. Some basic linear algebra, then we move on to principal component analysis and eigenvalue decomposition and single value decomposition. So these are the three topics we cover with some basic linear algebra. So that is the topic of this presentation, this problem solving session as well. So we'll be going through that. Now, so a matrix is given, x a vector is given, you apply transformation ax and obtain a new vector, which is the following ways. Discuss the geometric effect of this matrix transformation on the vector x. So this is what they are asking. So um, so what we can do, first thing is like, let's just multiply this one and see for ourselves. Okay, so 6 and 1 7 and 2 and 3 5. So the vector has clearly changed. Okay, further, uh, one thing we can do is subtract and calculate the eigenvalues here. Okay, x minus 1 whole square minus 4 equals to 0, plus minus 2, x is equals to 3 comma 1. Okay, Satish, as you came, so this is the question I have, the first question I have to solve. And the transformation a linear map, a matrix multiplication has happened to this vector x. Okay, and which describe best the effect of what has happened. Okay, so first I multiplied and then I calculated its eigenvalues, which are 3 and 1. So further, so if put the eigenvalue 1 here, okay, okay, to get the eigenvector, what we have to do is consider x and y, okay, and then do it like this, okay. Uh, so this is x plus 2y, and this is 2x plus y minus xy. This becomes 2y and 2x. So as we can see, for eigenvectors, for it to be eigenvectors, they have to be in ratio 1 is to 1 or 1 is to minus 1 here, okay, which is not there. In case of eigenvectors, there are no rotation happening, only scaling, okay, so it will be more both rotation and scale, okay, the direction changes, okay. This is our answer. This is the problem we're having here. So let's consider the eigenvalue as lambda. Okay, so lambda 1 1 is equals to this matrix, which is 1 2 1 1, and so it is the eigenvector of this, but let's do it methodically. So this is 3 and this is 2. So no, this is not the eigenvector, this is not possible. Cha. this is the what we have here, and lambda is the scalar here, ax is here. Acha. So we have seen the eigenvalues that are possible are 1 and 3. Okay, so okay. So there was some little confusion there. So let me clarify this properly. So what we have here is this 1 2 2 1 1 2 2 1, and so the eigenvalues, as you can see, 1 minus x, 2 2, 1 minus x. Determinant of that is equals to 0. So x minus 1 square equals to 4, x equals to 1 and 3. Right, so this is the answer we have. Now for each eigenvalue, what I'm going to do is that I don't know the vector here. Okay, so I consider this as x, okay, the vector, and the lambda, okay, and then lambda is here, okay. So 1 minus lambda 2 2, 1 minus lambda, okay, and into this vector x is equals to 0, right? So for 1, we will see that 0 2 2 0. Okay, suppose this is x1 and x2, so you get two equation, x2 equals to 0 and x1 equals to 0. So here x1 can be anything. Is it correct? This is minus 2 2 plus 1 minus 1 3. Actually minus 1 and 3 is there, okay. So this is minus 1, this becomes 2, right? Okay, so this is the mistake we had, actually, that's why the confusion. Okay, so now this is the x1 plus x2 is equals to 0, and x1 plus x2 equals to 0. So one eigenvector we get is 1 and minus 1. This is the form. You can also normalize it, okay, for the eigenvalue minus 1. Okay, so if the eigenvalue is 3, okay, so we have the matrix here 1 2 2 1. This is the one, right? And the eigenvalue is 3, okay. So from the diagonally we subtract the 3, okay, so this become minus 2 2 2 and 1, okay. Then we have our variable x1 and x2. This is equals to 0, right? So we have x1 equals to x2, right? This is the expression we have. So the eigenvector here is for the eigenvalue 3. Okay, so these are the two eigenvalues and vectors we have here. Okay, and the first question, as you can see, is like so they've given this vector. Okay, if it was the eigenvector, it will only scale. As it is not the eigenvector, so it will scale and change direction both. Okay, so question number 2 we have is, so student claims that the x is the eigenvector. So we've seen it is the eigenvector for the eigenvalue 3, and so that is the answer. Okay, a company models user transaction between two platform APX and APY using a matrix this. Each day users switch between these apps according to the matrix. If on day 0 300 users are on app X and 200 on app Y, which of the following best described what will happen to the distribution of user? Okay, so this is the problem we're having here. So m is equals to, so as you can see the problem, let me take the screenshot again. I think that's the better idea. So as you can see, this is 0.7, 0.2, 0.3, 0.8. So this is the matrix we are having. Okay, and on a day, on day 0, okay, 300 users on app X, okay, and 200 on app Y. So what will happen, what will eventually be the distribution of users? Okay, so the thing is that, so what happens, so we've seen in the class example that this converges to, so let me show you. So first let's calculate the eigenvalues and eigenvectors for this, then we'll get a better idea. Okay, so let's do the eigenvalues. Eigenvector may not be required, I think. Let's determine it equals to 0. Okay, so x minus 0.8, x minus 0.7, and 3 to 6, 0.6, 0.06 is equals to 0. I square this up and this becomes 1.5x plus 856.6, okay, minus 0.06 equals to 0. X square 1.5x, and this is 0.5. So 1 into 0.5, this becomes, okay, so x minus 0.5 and x minus 1, so this is equals to 0. So x equals to 1 and 0.5. So we have seen that if the dominant eigenvalue means the maximum eigenvalue is 1, then it converges to the dominant variable. Okay, okay, given matrix this, so find the dominant eigenvalue of A, which is the bigger one. Okay, that is what we will find, 4 1 3 2. Okay, so 4 1 3 2, 4 minus x 1 3, 2 minus x, this is the matrix we have, x square minus 6x plus 4 to 8 minus 3 equals to 0, x square minus 6x plus 5 and 1, x equals to 1 and 5. Done. The dominant one is 5. If the following statements are true, the eigenvectors corresponding to different eigenvalues are linearly independent. So that is correct. Okay. Eigenvalues of square symmetric matrix are orthogonal. That is also correct. Okay. Eigenvectors of a square symmetric matrix can thus form a convenient basis. That is also correct. A statement which is wrong. What type of question is that? Okay, so a very simple one. Okay. Now question number 6 we are having. There's a vector, the matrix is there. Which one? What will converge to? This we have seen, like it converges because the eigenvalue I have seen here is the multiple of the dominant eigenvector of A. So let me show you how it is done. So here, as you can see, so for square matrix you can see the calculation here, that it for pth one it is equals to k times the ed. Okay, p plus 1 is a times of that. Okay, then it becomes like this, k times. So as you can see, so this is the scene we have, and the question is, what does it converge to? Okay, so multiple of the dominant eigenvector of A. Okay, so that is it, but it depends on if the dominant eigenvalue is 1 or more than 1 or less than 1. Okay, these are the problems we are having. Let's take a screenshot again. So data scientist is simulating a simplified web graph with 3 web pages. The transition probability matrix for a web server moving from one page to another. Each column represents probability distribution is modeled as this. Achha. One page to another. Random vector distribution vector to this. Okay. Ishino repeatedly applies the transformation vk1 is equals to mvk. Sure. Okay, what kind of matrix is M? Why is this classification important for understanding the long-term behavior of vk as k tends to infinity? Okay. So we will do the eigenvalue decomposition, but first we can understand the square matrix. That's for sure. Now we will find the eigenvalues of this. Okay. Okay. we're going to do x minus 0.5, okay, the 0.5 minus x, okay, and next what we're having is x minus 0.4 into x minus 0.5 minus 0.09. Okay, then minus 0.2 into 0.3 into 0.4 minus 0.3 into 0.2 plus 0.3 into 0.09 minus 0.2 times 0.5 minus x. Okay, so the point is that, so is it a symmetric matrix? So it is a symmetric matrix, is it? No. It is not a symmetric matrix. Eigenvalue has to be calculated. It's not. It is a long calculation, honestly. I think the maximum will come to 1. Okay. Suppose after multiple iteration, the vectors V converges to this, which the following best interpret the result in the result of the web ranking. Sure. So this is the one. Okay. So it denotes the which pages has the most likelihood of visiting. So that is it. Suppose instead of starting with v0, it's time to start with v0 equals to this. Which will the final ranking vector after many iterations be different? It will not be different. Okay, because uh, let's see if it will be different or not. So it converges to, as you can see, k into eigenvalues. Okay, so eigenvalue is 1, so k is the how many times it has been done. Okay, it does not depend on v, I think. K, what is k here? 0. So it doesn't depend on v, at least, so answer will be false. Okay. Okay, now the question number 10 we are having here. A weather model predicts transition between two states, sunny and rainy, using X0 is the initial probability distribution across states. The methodology applied the transformation this with the following page describes the long-term behavior of the sequence xk. Okay, so that depends on what is the eigenvalue of this. So 0.6 minus x, 0.2, 0.8 minus x, 0.4. Okay, so x minus 0.8, x minus 0.6, actually, minus 0.08. So this becomes 0.4. and this is so answer is 1 and 0.4, right? So the maximum is 1. So what it means is that it will reach a steady state. Okay, it will converge, okay, to steady state probability vector. Okay, so that does it. The student studies the behavior of this function. She computes x1 is equals to this and x2 is equals to this. What is the nature as this sequence k becomes infinity? So what will happen as k becomes infinity? So we have to calculate the eigenvalues of this matrix. So how are we going to do that? So that's the usual thing. So x is 0.3 and 0.5. These are the two eigenvalues of this matrix. Now you have to understand that um, none of these are equal to 1, so it is less than 1. So in case of less than 1, it will converge to a 0 vector. Okay, so that is how the theory is there. Okay, given this vector, this determinant set this can serve as a basis for R3, which of the following step is the most appropriate step. So you have to check whether they are linearly independent or not. Okay, so if anyone can be written as a linear combination of another one, that means they are not linearly independent. Okay, so that's C. Check the determinant of the matrix this. Okay, so if you check the determinant of the matrix, okay, the sum is not enough. Okay, because the condition for linear independence is alpha 1 v1 alpha 2 v2 plus alpha 3 v3 is equals to 0 only when alphas each of them are equal to 0. Okay, so the sum doesn't prove anything, and so both A and C is the answer. Determinant part determinant part is for linear independence. So let's see about that. What's the interpretation there? So this is the matrix you're having, okay, of v1, v2, v3, and we're taking the determinant of that. Okay, the determinant can be also interpreted as like suppose there are x1, x2, x3, okay, three-dimensional yes, and this is equals to 0. Okay, so in this case I'm calculating the determinant. So what it means is that this is a linear combination, right? So the linear combination is equals to 0. Okay, only when x1, x2, x3 are 0. So that is the one. Okay, so determinant of that represents the linear combination. So we have done that. Okay, so that is why it is a valid one. Okay, so these are the two accepted answer. Next, what you're having is so this what is the determinant of A tells about the vectors. So determinant tells about whether they are linearly independent or not. That is what we've seen already. Okay, let's take the determinant of this and let's see what answer we get actually. determinant is 0. So for any value of x1, x2, x3, as we have seen, the sum will be equal to 0. So we did not want that. Okay, for only x1 equals to 0, x2 equals to 0, and x3 equals to 0, it has to be 0. Okay, when the the means scalars are all equal to 0, only then they are linearly independent. But even in this case, without any conditions on the scalars, um, the they are still equal to 0. Okay, so that is why they are linearly dependent. Okay, which of the following statement is always true for the matrix this and has distinct eigenvalues? So eigenvectors are linearly independent. Okay, so it's very simple. Why are the eigenvectors of a square symmetric matrix considered special? Because they're orthogonal. Okay. Let A be a real symmetric matrix which the following statements is true. So it's a real symmetric matrix. So that is direct correlation here, which maximizes is the largest eigenvalue. Okay, like that. Next we are having so let's do this questions now. So the question is, do the following statements are true regarding eigenvectors and symmetric matrices? Eigenvectors correspond to different eigenvalues are linearly independent. So we have seen that is correct. Eigenvectors of any matrix are always orthogonal. That's wrong. Eigenvectors of a square matrix are orthogonal. Square symmetric matrix are orthogonal. That's correct. Eigenvectors of a square symmetric matrix can form a basis. That is correct. Okay. Next, web track is analyzing data. Okay. This is the data we are having. Calculate the Pearson correlation coefficient to assess the similarity between x, y, and z. Okay, so the correlation coefficient is for every data set. This, what they have to do is calculate xi minus x bar, okay, and yi minus y bar under root, then the xi square minus x bar square. I mean RMS, I think. Okay. I mean the covariance divided by the variance of each. Okay, so that is the formula. Okay. This is the formula you have. Okay. This is summation over, okay, and summation over yi minus y bar square. Okay, this is what we are having. Okay, next, so the calculation has to be done. It's not easy to be done right now. Okay, so that can be done. Now you're looking at data set with 100 features. After applying PCA, you reduce it to 2 dimensions. The new dimensions are linear combination of original features and orthogonal. So that is correct, right? Those are the conditions we have already. Okay. linear combinations and orthogonal. Okay. So data scientists analyzing EEG signal recorded from 100 channels, and these are the questions we are having. So let's see to that. Let me take small break. Okay, then I will see again. So we'll continue now. These are the questions we're having. A fintech startup is building a real-time fraud detection system based on thousands of transaction features. High-dimensional data is slowing down model training and inference to resolve the data science team applied PCA and returns only the 25.25 principal component from the original 300 features. After transformation, they observe the components are uncorrelated systems are much faster fraud resistance. Okay, best explains. Not like that. Second point is PC transfer the features in new space or components uncorrelated of a high variance direction and preserve reduce the damage to the name. So this is the one. What mathematical guarantee offered of PC ensure the model is not negatively affected by the redundant overlap, minimizes the um, so this is the one. Okay, you can notice that of grayscale human faces, each image is given total number of images 500 pieces related to dimensional computing the top 100 eigenvectors of extra transpose X. So what they're saying is that you have 100 cross 100 pixel images, okay, and 500 such images. So we need top 500 eigenvectors of X transpose X. So X is the data matrix here, so X transpose X, okay, and okay, and the dimension, as you can understand, is the number of features. So that is like 10,000 cross 10,000, okay. So this matrix only top 100 eigenvectors are to be taken, okay. So you're doing 10,000 cross 10,000 matrix X transpose X. So we're going to do eigenvalue, I mean principal component analysis on that, okay, and only take the top 100 eigenvectors, okay. Each eigenvector is reshaped into 100 cross 100 image, okay. That eigenvector, okay, again of dimension 10,000 only, it's reshaped into this, okay. So this is a lower dimension basis to represent face images efficiently. You have 500 images each, originally 10,000 dimension. After projecting top 100, how many scalar values are needed to store all 500 compressed images? What is the correct form of the singular value decomposition of the real matrix? This, okay. So this is the problem we're having. So this is the, okay, first option is the correct one, okay. It is definition. What is the, it is upper triangle, okay. A diagonal matrix with non-negative real numbers, as you can see in the formulation we're having here. Okay, this K cross K matrix has to be like diagonal matrix non-negative real numbers. Okay. In the case of eigenvalue decomposition, that was the and in this case actually in SVD, this the values, the real numbers, are actually square root of the eigenvalues. Okay, that's a given fact. Okay, so we're going to finish off. So we were about to finish off actually. Razul, okay. Today's session is done. Do you have any doubt yourself? Any doubt you're facing? Okay, we'll close it off here. Okay, thank you. ये बड़ा करो होगा उसमें सर